Hello, everyone. It is so exciting to be back at ElixirConf this year, although this time it's virtual because of what. My name is Sheharyar. I'm a software engineer from Lahore, Pakistan, and I've been writing Elixir for about 6 years now, and have been in the industry for about 11. Currently, I'm a backend engineer at Slab, which is a knowledge base for teams, making it easy to share and organize critical knowledge. Other than that, I also manage the Google Developers Group in Lahore, supporting the emerging developer community here through various programs. So let's start with a bit of background. As part of my work at Slab, we built this beautiful real-time collaborative editor, much like Google Docs, allowing users to work together on the same document. Early on, much of this was made possible because of Elixir and Phoenix's excellent support for building fault-tolerant and real-time systems out of the box, giving us a solid foundation to work with. But as you'd expect, we still had to solve some very interesting challenges, including real-time collaboration and consistency of data. So let's talk about what we want to accomplish today and how we're going to do it. This talk today will focus on the core unique concepts around real-time collaboration, leaving out extra features like persistence, authentication, or rich text formatting. We will, however, discuss some common problems around collaboration and how to solve them, including the bare minimum user experience we need to support. We'll do this by first discussing what a high-level architecture would look like. Then we'll jump right into the code, implementing a bare-bones structure needed to support the document server we'll later implement. This server will be responsible for managing and updating a document's contents. And we'll do this in multiple iterations, solving each problem we encounter until we have a seamless collaborative experience. I'll show some code, but don't worry, I'll put a link to it at the end. Fair warning, this is going to be a pretty demo-heavy talks, and I'll be switching between the slides and the app quite often. For the high-level architecture, what we desire is something like this. Leveraging Elixir and OTP strength in managing processes, we'll use a GenServer for storing the state of a document and performing updates to it, making one process the authority per document. These document processes will be spawned under a supervisor, so they're monitored and restarted in case of any unknown errors. With this, Elixir will pretty much handle scaling for you. You could open tens of thousands of documents and Elixir will evenly distribute them. On a high level, the server and the client each maintain a copy of the document. When the client makes a change, it sends it to the server over a Phoenix channel. This is then forwarded to a GenServer, which applies the change to the document, updating the contents. If successful, it sends back an acknowledgement to the client and also broadcasts the change to all other connected clients. The part that will handle real-time collaboration is a document GenServer. We'll look at how one would approach implementing the core of a collaboration system in a bit. For completeness, let's go over the basic moving parts first. Starting with the web page itself. We'll create a simple web page and the corresponding route, controller action, and template. This will allow users to open any document by typing the ID directly in the URL. Since we don't plan on supporting rich text formatting today, all we need is a plain text area element in the template. This is where the users can write and collaborate on content with a bit of styling. So with a bit of styling, it should look something like this. So as you can see, it's a pretty simple page with just a text area. For document GenServer, we'll go with a simple API. We'll export a getContents method to fetch the current document, and also an update method to perform any changes to the document. We won't implement their callbacks just yet, and instead come back to this later when we are ready to add collaboration. There's also an open helper to find or create a document for a given ID. This will make each document process an authority per document. We also need a supervisor that can spawn and supervise these document processes at runtime. Elixir's dynamic supervisor is the right tool for the job, and we'll use a super simple bare-bones implementation for our use case. We want the supervisor to start with the application, so we're also going to add it to the application supervision. For the networking layer, we'll create a plain feeds channel for the document topic. When a new user connects to a channel, the join callback is called which pattern matches on the document ID. It calls the open method on the GenServer, creating the document if it doesn't already exist. Immediately afterwards, it pushes the current contents of the document to the client in the after join callback, bringing the client up to date. We also need to define a callback to set the update events from clients. These will be offloaded to our document server, which will do its magic. And the final result will be broadcasted to all of the connected clients. So I'm quickly going to show our Phoenix channel to you. So as you can see, it's a simple channel with only one event handler. At this point, I want to highlight the fact that Phoenix has a very solid implementation of WebSockets. Other than directly replying to the client that sent you a message, it also gives you concepts of things like broadcasting and presence basically for free. This is something you might have to otherwise implement manually for other platforms. Finally, getting to the document server. So let's start with a naive approach one might take to implement such a system. That is, send the entire document on each update. In the documents GenServer here, when get contents is called, we will directly return the document contents. This will allow the client to initialize the editor with the latest contents. Whenever a client wants to update the document, it sends the entire contents of the document. The GenServer will maintain this in its state and also return it to the document channel so it's broadcasted to other clients. Here's a very simple implementation of our client. So it's in JavaScript. When the client starts, it connects to the Phoenix channel and sets up various DOM and channel event listeners. Initially, and on every update, it receives the latest contents it receives the latest contents and displays them in the editor. And when a local edit is made, it pushes the contents on the channel. So I'm just going to restart my Phoenix server here, just in case. And I'll refresh this. So trying this out. So I have two editors which have the same document opened. And it seems to work really well whenever one client is typing. But what if multiple clients type at the same time? We can simulate this by adding artificial latency. And I can do that here by just adding a simple set timeout function. So if I make two changes in parallel here, so I'll type something like 1, 2, 3 and 4, 5, 6 here. As you can see, when that happens, the changes from the clients are lost and the local documents now have completely different values. So there are two issues with this approach. The most important one is that when multiple clients type at the same time, the older edits might get lost. And as a document grows, so will the bandwidth needed to push it to everyone, which will also affect response times. For a large number of clients and changes, this can explode. So this doesn't actually do what we really want. The solution here is pretty simple. We can send the individual edits that each client makes in the form of diffs instead. This way, we can apply all edits to the document when multiple users are typing, so we won't lose any changes. And we will be able to reduce the bandwidth since diffs will usually be a fraction of the size of the document. So let's do that now. We'll keep our get contents callback the same, but modify the implementation for our update callback. Here I'm using a library called Delta for this purpose. I'll go into more detail about it in just a bit, but for now, all you need to know is that it can represent documents as a list of changes in the form of inserts and deletes. It can compose new changes on top of existing documents as well, resulting in a new one. For this, we'll also need to change the default contents value to a list. In update, we'll now apply the change to our document via delta.compose and also return it so it can be broadcasted to all of the clients. So let's try this out. So I already have the code for this change written. And I'll just switch to that branch. So here's the updated document server with the new changes. And this time we're using delta.compose to combine this into a new document. So I'll type something here. So let me just refresh this whole app. Yes. So again, it seems to work. As you can see, we retained both edits. But let me introduce some latency again, and let's see what happens. So go back to my channel and my client and introduce latency via timeout. So if I make two changes in parallel, I'll write something here and something here. As you can see, we returned both edits, but the document has still diverged. We can see this again with the classic goat example. So I'll type A here and I'll type T here. Or one here, two here. So even with a single corrected change, both clients now show different values. So why is that the case? This is because by the time the second client's edit reached the server, the original document had already been updated and the edit is now outdated. These changes are also broadcasted to all clients, so the diffs received by each client are no longer accurate, resulting in different contents in each editor. To fix this, we need some sort of a consistency model. Let's think about this for a bit. Why exactly do we need one? No matter how fast your networking layer is, there will always be delays and even disconnections. For a real-time collaborative editor, users must immediately see what they typed on their screens. When multiple people are typing at the same time, each of their changes should be applied locally, even if those changes haven't reached the server yet. But eventually, all of them should be looking at the same document with all of the changes combined. A consistency algorithm allows us to do this by resolving conflicts on the clients and server to ensure the data is the same everywhere, or it eventually becomes the same. Enter operational transform. Operational transform is a technology for handling consistency and conflict resolution. While there are many other algorithms and solutions that attempt this, OT has proven to be extremely well suited for collaborative text editing over the years. Among many others, Google Docs also employs OT to power the real-time collaboration. It's used by comparing the client and server document versions to figure out if a diff is outdated. Then it transforms that diff by looking at other changes performed since, essentially resulting in a new edit that seems like it was sent from the latest version of the document. I'll show this in just a bit. At the time we were first building Slab, a good implementation of OT did not exist for Elixir. Since the Slab team already had prior experience working with OT as part of building Quill and the Delta libraries for JavaScript, we ended up writing one for Elixir as well. We recently open sourced Delta for Elixir, which is a format that can track a document's contents and how it changes over time. It does so concisely and without ambiguity by using only three constructs: insert, retain, and delete. It has full support for operational transform, allowing for a consistent document model across all platforms. Other than tracking contents, it also supports rich text formatting and tracking arbitrary attributes like author, time, comments, and more. But we won't use Delta for those today. Although we've just released this to the public, Delta has been a core technology at Slab for the past 4 years, so we're quite confident about it. So back to our document server implementation. This time we're going to transform received diffs as well. First, we need to redefine our GenServer state, since we now need to maintain the number of revisions as well as all the changes made to the document so far. For the get contents callback, we'll now also return the version along with the contents. This will allow the clients to know which version the document is at during initialization. Finally, for the update callback, we first need to calculate how far behind the client is by comparing the client and server versions. We can then pull all the recent changes the client doesn't know about yet from the GenServer state. The edit sent by the client will be transformed on top of these intervening changes, resulting in a new transform change that looks like it was sent from the latest version of the document. And it can now finally be applied to the document using Compose. We'll also update the state, pushing this new transform change into a changes list and incrementing the version number. This new transform change and the updated version will be returned to the channel and broadcasted to all connected clients. For OT to fully work, we also need to transform on the clients as well. Because when receiving an update from the server, the client might have pending edits that are not pushed to the server just yet. So I'm using the JavaScript version of Delta here, doing basically the same what we just did on the backend. So let's try this out again. Again, I have the implementation for this already in a separate branch, so I'll just switch to that. I'll restart the Phoenix server. Okay, so I'll go over the code. So we have the new document GenServer here with transform. In the update callback, we first calculate how far behind the client is by getting a difference of the client and server versions. Then we pull all those changes from our changes state and transform the newly received client change on top of these intervening changes one by one. Finally, we compose the new transform change on top of the current document's contents, resulting in a new document, and also update the version and the changes. On the client side, we have something similar. So on receiving a new change from the server or another client, we transform that change using delta.transform and finally compose it onto the contents. So I'll refresh these. So I'll type something again. Again, everything seems to work, but we won't know for sure until we add latency again. So let's do that. Again, I'm adding a latency of 2 seconds using set timeout. Just to make sure, I'll refresh. So typing different characters in 2 different clients. After the delay, the documents on both clients converge to the same state, displaying eventual consistency. And this will remain true no matter how many clients there are. But let's type some more. So you might have noticed something, that there's still a minor issue here. So even though the document is not consistent on every client, our cursor was jumping around. When multiple users are making changes to the same document, we are not able to figure out where the cursor should be. So which doesn't exactly say seamless real-time collaboration. The good thing is this can also be fixed by operational transform. OT can also be applied to indexes and not just contents. By using Delta's built-in transform position helper, we can calculate the new position the cursor should be at. So let's make a minor change to our JavaScript code. After the edited contents are updated, we can set the new position of the cursor in the text area. So Again, I have the change for this already. I'm just going to switch to that branch and restart my Phoenix server. The only new addition here is that we get the text area's current cursor position and then transform on it using the previously transformed delta we already had. Then we just add, then we just set the new cursor position in our text editor. So trying this out again. So if one user is typing something here and the other user is typing something here, the cursor for the first user should be retained in the original position or where we expect it to be. Okay, so what's next? So we've only begun scratching the surface of what makes a great real-time editor. There are other challenges that we couldn't go into today, but I'll encourage you to think about some of these. The most popular would be adding rich text formatting to bring our newly created app a little closer to what Slab or Google Docs do. The good news is that the Delta package already has built-in support for this, so you won't have to change a lot to achieve this. Another problem to think about is persistence. At some point, we need to save the data to a DB, but what to store and how often to store it? How would you handle unexpected errors and GenServer crashes to store the data before it's lost forever? Another cool feature would be showing the cursor of other connected users to show if and where in the document they're typing. You don't have to go too far for this either, as Phoenix presence can do the heavy lifting for you. There's a lot more that's possible, like buffering edits to reduce bandwidth, making it survive sudden restarts for zero downtime, adding author attribution and comments, and even collaborating on embedded data. If these challenges sound interesting to you, do come find me in the conference app, and I'd love to talk more. So feel free to post the questions in the conference app, and I can get to them later. I've put up some links here for a live demo of the app we just built. There's also a link to these slides with the code and the Delta package for Elixir. If you want to reach out, you can get in touch via email or find me anywhere at Sheharyar. And finally, we're also hiring at Slab. So if you're interested in what we're doing, do reach out. Thank you.